Today we're going to find the integral of the flow function with respect to dx. But of course, we have already done a video about finding the integral of the flow function where we start off with the basic version. Inside the flow function is just simply x. And we actually get the results up here. This time we're going to make a little change here and then try to make it a little bit more challenging by finding the integral of the flow function where inside is a times x, and again we are assuming that a is just some constant number, and of course if a is equal to 1 we just get the first case that we actually have up here, and if a is equal to 0, again it will be very boring because the whole thing is just turned out being 0, and then you will have the integral of the 0 function and then with respect to dx, and then we just get a constant. So here we're going to set a as not equal to 0 nor 1 and try to find out what's going on here. And for now, we can assume that a is positive, so that we're going to look at the first case. And then you can try the negative version yourself. But before we move on, you can pause the video and try it first, because we're going to see the solution in 3, 2, 1. All right, so what we're going to do, we're going to use the same trick that we actually used to find the integral of the flow function with, of course, x inside, by using the fundamental theorem of calculus part 2, which says that we can actually rewrite this antiderivative as an integral I, where this integral, we're not going to get a definite integral. We actually have 0 to some value of, in this case, x. And now we're going to change the inside, the function, into the flow function of a times some dummy variable. Let's call it u here. And then, of course, we're going to take the integral with respect to u now. Then how are we going to do? What should we do next? Now we can actually try to think of the graph, which is actually similar to the flow function that we have, the basic flow function. But instead of having the width of each interval to be exactly equal to 1, which is from 0 to 1, 1 to 2, so on and so forth, of course, except maybe the last part, we now actually have to slightly change a little bit by adjusting it with 1 over a as our width. Why? Because we can see that if we try to plug in 1 over a, we actually will get a times 1 over a, which is equal to 1, and then that will actually give us the flow, the end result of the flow function actually get increased by 1 every time. So in fact, this is what we're going to get. If we start from 0 to 1, we actually have the results of this interval, or the y value of the interval, would be equal to 0, where from 1 over a to 2 over a, the results will be equal to 1, so on and so forth. So we're going to list a few as an example, and then we're going to see where the ending behavior of this function within the interval from 0 to x going to look like. So our most right endpoint is of course x. Then what would be the y value when u is equal to x? Of course, we just substitute back in here. We should actually get the flow of ax for when u is equal to x. Then we need to now consider where is the left endpoint of this small interval would be at. In other words, once we found the left endpoint, we can actually see that the second of the last interval that we have should also have the length of 1 over a, just like what we expect down here at the beginning. Then, of course, in this case, the left part doesn't really matter. We know that this width here is equal to, or the length of the interval would be 1 over a anyway. But what we do care is to find out this u value that we need to actually help us break it out this integral into two parts. So before we figure out this one, we also need to know that what is the y value of this part of the interval would be, or what is the height of this rectangle is going to be. Well, if we look at the graph, we can easily tell that the height would be 1 less than the highest interval, which is up here. So the height will be the floor of ax minus 1. Then we actually could collect all these parts here, and seeing that it's just sum of all the rectangles, meaning now we can break this integral into the first part in pink, where we have the, again, dummy variable, let's call it n, from 0 all the way up to this height here, the floor of ax minus 1. And then we're just trying to add up the areas of the rectangles that we have. And what's the area? It's just the length times width, or the height times the length of the interval. What is the length? Again, it would just be 1 over a. And what is the height of each rectangle? Of course, it's just the n value that we set up. So in fact, we actually get the first part, or the pink section here, to be the sum of n over a, where n starts from 0, go up to the second highest point that we have in the graph. Okay, now we need to figure out the remaining part, which is in the form of integral. So again, now we can see that this part is also a rectangle. What is the width? Well, the width would then be from the left end to the right end. Of course, the right end is what we have already found or set up, x, where the left end is what we need to find. And what is the height? The height is, of course, just the same as it's a constant, it's just the highest value that we have, or the maximum, which is the floor of ax. And we're actually taking it with respect to du. So last part that we need to aware of is how do we actually need to find this left endpoint? Well, let's notice that in order to have the change here, we need to make sure that this a times u is actually going to be equal to this value up here, which is same as the floor of ax. So because u is actually related to the floor as well. So we actually will have a form that u has to be something divided by a as the minimum value that can actually satisfy this. So what value could make it work? Well, here is the value. So how does it work? Well, we can see that this has to be the smallest value that we can accept, so that the a will cancel, and we know that the floor of the floor is actually the floor itself, because again, this part is already an integer. No matter what we are trying to take as a floor function, it's still the integer itself. So this will be the smallest value that we can have. Anything smaller than this will actually make the left hand side is not equal to the right hand side. So that's how we actually can find the lower bound of this partial integral here. So what's our lower bound? The lower bound will now become just this value, the u value that we have, which is the floor of ax all over a. Good. So we're going to continue. So we can see that for the second part, it's just a rectangle. And a rectangle will actually give us the area, length, which is actually the height here, times the width, which is the length of the interval, which is the upper bound minus the lower bound. where our first part is, in fact, 1 over a is a constant value. The only part that's changing inside of the the sum here, the summation, is the end part. But that is, in fact, a sum of integers up to this value here. So we can actually use our formula, which is saying 1/2 times the n value, the last n value that we have, times the last n value plus 1, which is again just simply the floor of ax. So now we can just try to put everything together and then try to simplify some stuff. So we see that here it has 2a in the denominator. There's an a here, so we can factor out the 1 over 2a, and then we can factor out the floor of ax. So we can see that the first part has just this thing here. Everything is out of parentheses remaining. And then for the second part, we factor out this, and then we factor out 2a, 1 over 2a. So the x will turn out to be 2a times x, and then minus, we factor out this, and then we factor out the a. We actually factor one more 2 on the denominator, so we actually will get 2 on top times the numerator. And then we can just try to gather the things up and make it look nicer to get 2ax. And then we have minus 2, and then we have plus 1 copy, so we have minus 1 copy and overall, and then minus 1 as the factor inside of the red part. So this is an indefinite integral starting from 0. So what is the antiderivative in general? The antiderivative of the floor function of ax with respect to x itself will just be the results here. And of course, don't forget, as an antiderivative, we always need to put the constant plus c.
Thanks for watching. I'll see you in the next video.